Welcome to the CCNA 200 to 301 version 1.1 video series. Today we are breaking down Domain 1.0 network fundamentals, specifically looking at Objective 1.1, which covers the role and function of various network components. Let us jump right in. Objective 1.1a explains routers. A router is like the GPS or post office of a network. Its primary job is to connect different networks together, such as connecting your home network to the internet. Routers operate at layer 3 and use IP addresses to decide where to send data. For example, when you send an email to a friend across the country, a router looks at the destination IP address and chooses the best path to get it there. Moving to Objective 1.1b, which covers layer 2 and layer 3 switches. Think of a switch as a smart power strip for data. A Layer 2 switch connects devices like computers and printers within the same local network using MAC addresses. For example, a switch in an office building connects all the desktops on the third floor so they can share files. A Layer 3 switch does everything a Layer 2 switch does, but it can also perform routing tasks between different parts of a network. Now for Objective 1.1c, Next Generation Firewalls and IPS. A firewall is the security guard at the gate of your network. Traditional firewalls only checked the source and destination of data, but a next-generation firewall looks inside the data to see what it is doing. For example, it can tell the difference between someone watching a helpful YouTube video and someone trying to download a virus. An IPS or intrusion prevention system is an active alarm that automatically blocks a hacker the moment it detects a suspicious pattern. Objective 1.1d covers access points. A wireless access point, or WAP, is what provides Wi-Fi to your devices. It takes the wired signal from a switch and turns it into a wireless signal. An example is the small device you see mounted on the ceiling of a coffee shop or airport that allows you to connect your phone to the internet without a cable. Next is Objective 1.1e controllers. In large networks with hundreds of access points, it is impossible to configure them one by one. A wireless LAN controller is a central brain that manages all those access points from one place. For example, a university IT manager uses a controller to update the Wi-Fi password for every building on campus at the same time. For Objective 1.1f, we have endpoints. An endpoint is any device at the very edge of the network that a person actually uses. This includes your laptop, your smartphone, a VoIP desk phone, or even a smart thermostat. These are the devices that send and receive the data that the rest of the network hardware is designed to carry. Objective 1.1g focuses on servers. A server is a high-powered computer that provides a specific service to other devices on the network. For example, a file server stores all the company documents so everyone can access them, while a web server hosts the website you are currently viewing. Servers usually run for years at a time without being turned off. Finally, Objective 1.1h is Power over Ethernet, or PoE. This is a clever technology that allows a network cable to carry both data and electrical power at the same time. A great example is a ceiling-mounted security camera. Instead of needing a separate electrical outlet on the ceiling, the camera gets all the electricity it needs directly from the switch through the single Ethernet cable. That concludes our look at the hardware components in Objective 1.1. Continuing with our series, we move on to Domain 1.0 Objective 1.2, which describes characteristics of network topology architecture. This is how we organize all those devices we just talked about into a working system. Objective 1.2a is the two-tier architecture. Imagine a simple two-level hierarchy. At the bottom, you have the access layer where your devices plug in. These connect directly to the top level, called the collapsed core. It is called two-tier because the core and distribution functions are combined into one single layer of high-powered switches. This is very common in small to medium-sized businesses because it is cost-effective and easy to manage. Next is Objective 1.2b, the three-tier architecture. This is the classic design for large buildings or campuses. It adds a middle layer. You have the access layer at the bottom, the distribution layer in the middle to group floors together, and the core layer at the very top to move data at high speeds between different sections of the network. This design makes it very easy to grow the network without causing traffic jams. Objective 1.2c covers spine leaf architecture. This is a modern design mostly used inside data centers. Think of it like a web where every leaf switch at the bottom is connected to every spine switch at the top. This ensures that no matter which two servers are talking, they are always exactly the same number of hops away from each other. It provides massive speed and prevents any single switch from becoming a bottleneck. Moving to Objective 1.2d, we have the WAN, or Wide Area Network. While a LAN covers a single building, a WAN connects different cities or even different countries. An example of a WAN is a bank that has a headquarters in New York and branch offices in London and Tokyo. They use a WAN to stay connected over long distances, often using technologies like MPLS or the Internet. Now for Objective 1.2e, SOHO, which stands for Small Office Home Office. This is the simplest topology of all. It usually consists of a single integrated device that acts as a router, a switch, and a wireless access point all in one. If you work from a spare bedroom or run a small local shop with just a few computers, you are using a SOHO network. Objective 1.2f explains the difference between on-premises and cloud. On-premises, or on-prem, means you own and maintain the physical hardware inside your own building. You can see it, touch it, and you are responsible for the cooling and power. Cloud means you are essentially renting space and power from someone else's data center, like Amazon or Microsoft. Instead of buying a server and putting it in your closet, you access a virtual server over the internet. Moving to Objective 1.3, we are going to compare physical interface and cabling types. Think of these as the actual highways that carry our data. Objective 1.3a covers single-mode fiber, multimode fiber, and copper. Let us start with fiber optic cables, which use pulses of light to send data. Single-mode fiber is designed for long distances, sometimes stretching for miles between cities. It has a very thin core that allows only one path for light to travel, which means the signal stays strong and clear even over huge distances. Multimode fiber is used for shorter distances, usually within a single building or a data center. It has a thicker core that allows light to bounce around in multiple paths. While it is cheaper than single mode, the signal starts to blur if the cable is too long. Then we have copper cabling, specifically the twisted pair cables you see in most offices. Instead of light, copper uses electrical pulses. It is very affordable and easy to install, but it is limited to a distance of 100 meters and can be affected by electrical interference from things like fluorescent lights or heavy machinery. Now for Objective 1.3b, connections, specifically Ethernet shared media versus point-to-point. Ethernet shared media is like a group conversation in a crowded room. Multiple devices are connected to the same segment, and they have to take turns talking. If two devices talk at the same time, a collision happens, and they have to try again. We rarely see this today because modern switches have mostly replaced the old hubs that used this method. Point-to-point connections are more like a private phone call between two people. There is a dedicated link between two devices, like a router connecting directly to another router or a switch connecting to a server. Because the path is private, there is no risk of collisions, and data can flow much faster and more reliably. That covers the physical wires and connections that make our networks possible. Objective 1.4 focuses on identifying interface and cable issues. When we say an interface is not working right, it usually shows up as one of four common problems. First, let us talk about collisions. A collision happens when two devices connected to the same shared Ethernet media try to talk at exactly the same time. Think of it like two cars trying to merge into the same lane at once. They crash and the data is lost. While modern switches usually prevent this, we still see collisions on our interface statistics if we are using old hubs or if there is a hardware problem. Next, we have errors. Errors on an interface usually mean the data that arrived was corrupted or unreadable. Every piece of data has a unique math signature called a frame check sequence. When the data arrives, the switch checks that signature. If the math does not match, the data is bad and the interface records an error. This is almost always caused by a physically damaged cable or electrical interference. Third is a duplex mismatch. Duplex refers to how we send and receive data. Full duplex is like a phone call where both people can talk and listen at the same time. Half duplex is like a walkie-talkie where you can only talk or listen, but not both. A mismatch happens when one side of a cable thinks it is in phone call mode and the other thinks it is in walkie-talkie mode. This causes massive slowdowns because they keep interrupting each other. Finally, there is a speed mismatch. This is very simple. Both ends of the cable must speak the same speed. If one side is trying to send data at 1 gigabit per second but the other side is only capable of 100 megabits, they will never understand each other. Most modern devices use auto-negotiation to figure this out, but if a technician manually sets the wrong speed on one side, the link will simply stay down and no data will flow. Knowing how to spot these 4 issues in your device statistics will save you hours of troubleshooting. We are moving to the next topic, Objective 1.5. Comparing TCP and UDP. These are the 2 primary protocols living at the transport layer of the OSI model. While they both move data, they have completely different philosophies on how to get that data from point A to point B. 1. TCP, the reliable architect. First, let's look at TCP, or Transmission Control Protocol. TCP is a connection-oriented protocol, which means it is obsessed with reliability and order. Think of TCP like a high-stakes legal closing. Nothing happens until everyone shakes hands and signs the paperwork. This begins with the 3-way handshake. The sender sends a SYN packet to ask to connect, the receiver sends a SYN ACK to say they are ready, and the sender sends an ACK to confirm. Only then does the data start moving. But TCP doesn't stop there. It uses something called sequencing. Every packet is numbered. If packets arrive out of order, TCP rearranges them. If a packet goes missing, the receiver sends a retransmit request. The sender will literally wait and resend that specific piece of data until it is confirmed. This is why TCP is essential for things like web browsing, HTTP/HTTPS, file transfers, FTP, and email, SMTP. If you're downloading a banking app, you need every single bit of code to be perfect, or the app simply won't run. 2. UDP, the speed demon. Now, contrast that with UDP, or User Datagram Protocol. UDP is connectionless, often nicknamed the fire and forget protocol. It doesn't perform a handshake, it doesn't check if the receiver is busy, and most importantly, it never looks back. UDP has very low overhead. While a TCP header is 20 bytes long because it has to track so many things, a UDP header is only 8 bytes. It just attaches a destination port and sends the data as fast as the wire will allow. If a packet is dropped because of a brief flicker in the signal, UDP doesn't care. It's already busy sending the next one. This sounds unreliable, but in the world of real-time data, it's a lifesaver. Think about live video calls or online gaming. If you are in a match and a packet containing your character's movement is lost, you don't want the game to pause for 2 seconds to refetch that old movement. You've already moved to a new spot. You want the most current data right now. UDP provides that real-time experience for VoIP, streaming, and DNS. The summary for your notes. The trade-off is simple. TCP gives you reliability at the cost of speed, while UDP gives you speed at the cost of reliability. If the data must be perfect, like a PDF or a website, use TCP. If the data must be fast and current, like a Zoom call or a game, use UDP. Objective 1.6. Configure and verify IPv4 addressing and subnetting is where the logic of the network truly comes to life. In this session, we're going to break down how devices get their postal addresses and how we organize those addresses into manageable neighborhoods. What is IPv4 addressing? Think of an IPv4 address as a digital home address for every device on a network. It's a 32-bit number, usually written as 4 numbers separated by dots. For example, 192.168.1.10. Every piece of data traveling across the internet or your home Wi-Fi needs to know exactly which house it's going to. Without these unique addresses, your router wouldn't know if a Netflix stream should go to your TV or your neighbor's laptop. What is subnetting? If an IP address is a house address, then subnetting is the act of dividing a giant city into smaller, organized neighborhoods. By default, some networks are massive. If you put thousands of devices in one single room, one network, they would create so much background noise, broadcast traffic, that the network would slow to a crawl. Subnetting allows us to take a large block of IP addresses and chop it up into smaller, private sections. Why do we need to use it? There are three main reasons why network administrators use subnetting. Efficiency. It prevents address waste. If you only have 10 employees in an office, you don't want to give them a network block that holds 65,000 addresses. Subnetting lets you carve out a small slice of exactly 14 or 30 addresses. Security. It keeps departments separate. You can use subnetting to ensure that the guest Wi-Fi neighborhood cannot talk to the HR and payroll neighborhood. Performance. By breaking a large network into smaller pieces, you reduce broadcast storms. It keeps the local traffic local, making the whole system much faster. Learning the math. Now, a quick heads up, subnetting involves some binary math. You'll be looking at things like subnet masks, like 255.255.255.0, and CIDR notation, like /24. Because this is a visual and mathematical process, the best way to master it is through practice and watching live demonstrations. There are many fantastic, deep dive tutorials on YouTube that will walk you through the finger counting method or the magic number method, step by step. I highly recommend spending an afternoon with those videos to get the math down until it becomes second nature. In our next segment, we are moving to the next topic, Objective 1.7, Private IPv4 Addressing. This is a concept that almost everyone uses every single day without realizing it. To understand private IP addresses, you first have to understand the problem they solved, the Great IP Shortage. When IPv4 was created, there were only about 4.3 billion addresses available. As the internet exploded, we realized that wasn't enough for every phone, laptop, and smart toaster on the planet. The solution was to create private neighborhoods that could exist behind a single public address. 1. What is a private IP address? Think of a public IP address like your house's physical mailing address. It is unique in the entire world. A private IP address, however, is like an office extension or a room number inside a hotel. You can have a room 101 in a hotel in California and another room 101 in a hotel in New York. They aren't unique globally, but they are unique inside their own building. In networking, private addresses are used inside your home or office. They are non-routable over the public internet. This means if you try to send a package directly to a private address from the outside world, the internet routers will simply drop it. 2. The 3 reserved ranges. To keep things organized, the networking world agreed to set aside 3 specific blocks of addresses that can only be used for private networks. You will see these everywhere. Class A, 10.0.0.0, 10.255.255.255 huge networks. Used by massive corporations or universities. Class B, 172.16.0.0, 172.31.255.255 medium-sized networks. Class C, 192.168.0.0, 192.168.255.255 small networks. This is what you almost certainly have at home. If you look at your phone's Wi-Fi settings right now, you'll likely see an address starting with 192.168. 3. Why do we need them? Net. Since private addresses can't go on the internet, how do you watch YouTube? The answer is NAT, Network Address Translation. Your router acts as a translator. It has one public IP given to it by your internet provider. When your laptop with a private IP wants to go to a website, it sends the request to the router. The router swaps your private address for its own public address and sends it out. When the data comes back, the router remembers it was for your laptop and passes it back to you. The big benefits are conservation. Millions of homes can all use the same 192.168.1.1 address internally, saving billions of public addresses. Security. Since private IPs are hidden behind the router, hackers on the internet cannot see your laptop directly. 4. Practical practice. Understanding these ranges is one thing, but seeing them work is another. I highly recommend that you download Cisco Packet Tracer. It is a free tool provided by Cisco that allows you to build your own virtual networks. Use it for a practical demonstration. Drag in a router, a switch, and 2 PCs. Assign them private IP addresses from the ranges we discussed and watch how they communicate. It is the best way to move from theory to real-world skill.